Hello students, welcome to Arjun My Classes. So again we'll come back to this LPP by graphical method. Previously we solved one problem on this graphical method. Today we'll solve one more problem on that. As this is the problem, so it is given solve the given LP problem from the graphical method, and he given maximize z equal to 2x1 plus 3x2 subjected to the constraints. The two constraints he given, so that is 2x1 plus x2 less than equal to 12, and x1 plus 3x2 less than equal to 15, and x1 comma x2 greater than equal to 0. He given this LPP problem here. So what we do is here will just recap the method what we have to use. First step is what we have to convert inequality equations into the equality equations. Next work is once that process is done, next what we'll do, we'll identify the coordinates for the graph preparations. So we'll go for that method. Then once the graph preparation is done, then we'll identify the where we are going to get the maximum value, maximum corner, that we have to identify, and that will be our the z value, nothing but the optimal solution. And along with that we are going to represent that feasible region, so where exactly the location is there, that we are going to represent in our problem. Okay, coming to the problem, so first step is what we have to convert. So So what we'll do, we are going to convert this inequality equations into equal equations. The first proportion is this 2x1 plus x2 less than equal to is there. We are going to replace this less than equal to by equal to sign is equal to 12. And the second equation is we are converting this into x1 plus 3x2 is equal to 50. So we converted both the inequality equations into the equal equations. Is done. Second step is what? So we have to identify the coordinates of the graph. So here we have two decision variables here. These two variables we have to identify. We should know the value of x1 and x2 to draw the graph. So then what I will do, I will take the first equation here. So I will take the first equation, 2x1 plus x2 less than or equal to is given is equal to 12. So then what I will do in this, to identify this coordinate, I will put x1 as a 0 in the first condition, and I am going to get a value of x2. Second time I am going to make x2 as a 0, and I will identify the value of x1 as this one. So we identified the two coordinates to plot this graph for the first equation. Similarly, we will go for the second equation here. In the second equation, it is given as a x1 plus 3x2 is equal to 15. So then what we'll do, again we'll follow the same process here. Put x1 equal to 0 and x2 value will become 15 by 3. 15 by 3 nothing but it is going to become 5. So similarly, when x2 is equal to 0, then x1 is going to become 15. Means here we got two coordinates, and we'll go for the plotting of graphs. Graph. So we have a graph. So along x-axis we are representing this as a the x-axis we are representing it as a x1, and y-axis we are representing it as a x2. So coming to the first equation, we have to see this. When x1 was 0, x2 value is 12. When x1 was 0, x2 value was 12, and when x2 is 0, x1 value was 6. So we'll join both. Now we are going to join these two lines here. Sorry, once again I'll plot this graph. Right. Similarly, when x2 was 0, then we plot this one. Similarly, for the second equation, when x1 is 0, x2 value was 5. When x1 is 0, x2 value was 5, and when x2 is 0, x1 value was 15. So we'll join these two also. Yes, now we got an intersection here. So we can see this, that the problem, the given a conditions here, the conditions nothing but the constraints they given, less than equal to, less greater than equal to they given. No? So in this less than equal to, whenever it is the equation is having less than equal to, means the feasible region will be located below the region. Whenever we have greater than or equal to, the feasible region will be located above the line. Similarly, you just see this, two lines are given, 2x1 plus x2, 2x1 plus x2 less than or equal to 12 for the first equation, lesser than or equal to for the first equation. You just see this, the feasible region will be located below the region. Similarly, for the second one, x1 plus 3x2 is again less than equal to this one. It's also below the region. But for well, if we consider this region, for this for the first line it is below the region, but for the second region it will become above the region. If I consider this one, so then what happens, it will become above the region, because the line for the first line will be this side in between this. So then what we have to do is, we have to satisfy both the lines here. Now we just need to satisfy both the equations. So both the equations are telling that less than or equal to, the less than or equal to in this means, so we have to identify the below the line, whatever the reason will come, that one we have to check. So here this line I'm selecting, this is going to become below the line for both the both the constraint equations here. You can say this, for the first one also it is below the line, for second one is also it is below the line. So then what happens, this is going to become our feasible region. I will call this as a feasible region. So now we identified the feasible region. Next work is what we have to identify, where the maximum z value is located, that we have to identify. Maximum z value nothing but the maximum optimal solution we have to identify. So here we got a boundary, so here we got this boundary, and this one I will locate this one with a initial point as a, and this point I will call it as a b, and I will call this point as a c, and this corner as a d, right? So we got four corners, so we got four boundaries here. So then what we have to do is, we have to identify coordinates for all the regions here. For a corner, the coordinates are 0 comma 0. For the b corner, you just check, so b corner, the coordinates are 6 comma 0. Now for the c corner, you just once again glance on this you will make a perpendicular line here. So then what happens, this is around 4.5. C is equal to, along x-axis it is having 4.5. So then coming to this, it is around 3.5 approximately. I am taking it, when you go with the graphs, that time you will get exact results. And at D, point D, the coordinates are 0 comma 5. So we got all the four coordinates for the four corners. So now what we do is, we'll substitute these values into the z function, whatever we have the objective function here, objective function we have. So in that I'm going to substitute the values called x1 and x2. So for za, if I substitute a corner values into this one, so then optimal solution is going to become 0. ZB, if I go for this one, the maximum optimal solution, maximum Z will become, for this it is 2 into 6, it is nothing but a 12, because x2 is 0 here. So ZC, if I substitute 2 into 4.5, 2 into 4.5 nothing but it is 9, 4.5 nothing but it is 9, plus 3 into 3.5, 3 into 3.5 nothing but it is approximately it is 10 only, 10 point something it will come. So just we'll check that one. It is going to become 3 into 3.5. Substitute that, so it will come around 3 it is around 10. We'll get around 10. This is going to become what, 19. And ZD, if I substitute, so that value is going to become, so 2 is given 3.5 into 5, 35, 3.5 into 5 nothing but 35 in 3.5 into 5 here, what happens, it is going to become 5 5 is that 25 here, 5 3 is going to become 10.5. So then it is going to become, hold a minute, just yes, this is going to become, so this value is going to become 17.5. Means we got all the four coordinate corners. So then problem is subjected to what, the maximization. So then what we have to do is we have to select the maximum value in this all the four corners. So ZC is having the maximum value it is having. So then what happens, ZC is going to become our optimal solution. Then it is, then Z max is equal to ZC. So Z max is equal to what, is 19, and x1 is equal to, coordinates for that Z max are 4.5, and x2 is equal to 3.5. So this is about, this is the answer for this problem. Thank you.